So do you guys have any questions on where that negative square root of 7 is coming from? You good? You throw me a thumbs up or... Yeah, see, you guys can throw thumbs up around. Okay. So then if we want to know now any of these values, we have all the pieces. So cosine is going to be that negative square root of 7, the x over r, or the, if you want to consider the reference triangle, the adjacent over hypotenuse. Tangent is going to be the y over x, so we are going to have to rationalize that. So negative 3 square root of 7 over 7. The cosecant is really just this thing's reciprocal, so 4/3. Secant, the reciprocal of our cosine, negative 4 square root of 7 over 7 once we rationalize it. And cotangent is going to be this thing's reciprocal, so negative square root of 7 over 3. Everybody happy with those? Anybody have a question with those? That's going to be for a while a fairly foundational skill for us. So we want to make sure that being given one of the trig functions, we can figure out any of these, we are up to what quadrant we're in. Whether these are positive or negative really is going to depend on quadrant. So that is why we need this other information. Sometimes instead of being told this, you might be told that, say, your theta is somewhere between pi over 2 and 3 pi over 2. So this says we're in quadrants either 2 or 3. This says we're in quadrants 1 or 2. So it's essentially the same question, but you can be told it in terms of the value of the different trig functions. You can be told a range for your theta. Any other different ways you could approach that. Is there a way to do it with Pythagorean identities? Sure. Since we know, let me get rid of that. Since we know that our x squared plus y squared equals 1 is the equation of our unit circle specifically, and we associate these x values with our cosine values, so the cosine of theta squared plus the sine value for any particular angle squared, that has to be 1. This is that Pythagorean identity that Felix is referencing. And it's a nice tool. We'll use this tool a tremendous amount. That for a fixed angle theta, the square of the cosine plus the square of the sine has to equal 1 because we're on a unit circle. Even if we're not on a unit circle, the cosine being x over r and x over r, that r still cancels. So either way, the cosine squared plus the cosine squared has to equal 1. So this is a good solid truth. So one of the things you'll notice, by the way, is when we write cosine theta squared, when we write this, you'll often see it written as cosine squared theta. That's a kind of a shorthand for this. It tells us to square the cosine value, the output. We can't write it this way. If you write that square out without the parentheses out like this, then people will think the notation implies that you mean take the cosine of the square of our angle. So if you want to be taking the square of the cosine value, that square either needs to be outside of parentheses like this, or it needs to be on the function itself. So you'll see that notation pretty standard from pretty much from now on. So sine squared theta equals 1. So we could use this tool as well, since we know the sine is equal to 3/4. We could certainly use this to solve for the cosine of theta. Oops, that should be a plus. So the cosine squared of theta is equal to 1 minus this square, so 9/16. So that would be 7/16. Cosine squared of theta equals 7/16. So when we take the square root of both sides, we get that the cosine of theta is equal to plus or minus the square root of 7 over 4. That is the same square root of 7 over 4 as we got up here, but do notice we're given the plus or minus. This formula didn't know what quadrant we're in, so it gave us both answers. We'd have to recognize, Felix, that we're in quadrant 2, so I've got to pick the negative version of this. Also, now to find the tangent, cosecant, secant, and cotangent, we can still do those, but we've got to find the tangent by looking at the sine over the cosine. So for example, we know that, because this is as good a time as any to talk about these, we know that the tangent is supposed to be equal to y over x. And since the y value is our sine values and the x is our cosine values, we often think of tangent as being the quotient between the sine value and the cosine value. So if we wanted to find that tangent and wanted to use what we have down here so far, we could say that it's the sine, the 3/4, divided by the cosine, negative square root of 7 over 4. Multiply those by 4 to clear out the fourths. So 3 over negative square root of 7. And that's the same thing we got here before we cleaned it up to negative 3 square root of 7 over 7. So yes, you could use those identities to find all of these, and then use the reciprocal identities to find those. I'm not sure it's less work. It's different work. It's not even really different work. We're still using the Pythagorean theorem here. That 7 is really coming from the same place as the 7 came from up here. It is still the 16 minus 9. So that 16 sixteenths minus 9 sixteenths is still giving us the 7. So it's really the same exact tools, just in a slightly different set of orientations. So could you use it? Absolutely. Should you use it? Either way is perfectly fine. Felix, does that work for you? Yep, good. But yeah, that primary Pythagorean identity will expand this identity later on. But these are tools that you're going to want to start getting comfortable with. The idea that the cosine squared plus the sine squared, just because this is really the equation of our circle, that's always got to be true. That the tangent of theta is that ratio between the sine values and the cosine values. Correspondingly, we'll often see the tangent written as this thing's reciprocal, cosine theta divided by sine theta. These are collectively referred to as the quotient identities. This is one of the Pythagorean identities. We'll talk about the others later on. And they're, of course, in your text. And if you wanted to complete your current list of identities, the reciprocal identities, which we talk about fairly often, secant being 1 over cosine theta, cosecant being 1 over sine theta, and cotangent being 1 over tangent theta, we will collectively refer to those as our reciprocal identities. So we've been talking about some of those pieces, but that does kind of bring it together nicely. And your book talks in terms of those, but nice to have us discuss it. So that's a really good question to bring up right now, Felix. So thank you. What else you guys got? Anything else you guys want to look at before I start spieling away? You guys aren't going to be shy with me today, are you? Garrett, yes, we're going to be shy. Okay, I assume you meant yes. Yes, you're good. Okay, so let's back up here just a tad and build the tool we're going to use for some of our discussion today. So we have been talking a lot about this nice unit circle. Oops. So hopefully you guys have been practicing building this tool. If not, do try to make sure you are. I want a nice one here because I want to fill it with stuff and then I want to use it for some of our discussion today. So we talked about building these angles. So that was 0 radians all the way around was 2 pi radians. So halfway around was pi. You guys have seen me do this construction before. Half of that's pi over 2. If that's 1 pi over 2, 2 pi over 2s, this is 3 pi over 2s. Half of pi over 2 is pi over 4. If we count those around, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. So our pi over 4 radian measures. If instead of dividing by 2, we divide it by 3, that becomes pi over 6. And then 2 pi over 6 reduces to pi over 3. 3 pi over 6, 4 pi over 6 reduces to 2 pi over 3, 5 pi over 6. I know I'm saying this awfully fast, but again, you've seen this construction before, and ideally you're practicing doing this construction. So if you're not, I really recommend you do, because it will really help your intuition build up about radian measures. So questions about any of that? I know I did it fast, but I just want to use this today as a reference. Okay, we also built our 2 primary triangles. We built our pi over 3, pi over 6, pi over 2 triangle, so our pi over 3, pi over 6 right triangle, or in degrees, our 30, 60, 90 triangle. And we looked at the geometry of that and found that these side lengths, if we let this side length be 1, we could geometrically determine those other side lengths as 1/2 and the square root of 3 over 2. We did the same thing for a isosceles right triangle. So for a triangle with our, sorry, those should connect, but with our pi over 4 right triangle, if we did a similar kind of geometric argument with this side being 1, these side lengths with the square root of 2 over 2 and the square root of 2 over 2. So we went through and did those constructions. You guys remember those constructions? You happy with those constructions? You have questions about those constructions? We're going to make them important today. Pretty seriously important today. I'll take that as a yes, we're awesome, or we are frozen with panic, one of the two. Okay, so if we wanted to know, say, what the sine of pi over 6 was, or what the cosine of 5 pi over 4, or the tangent of 5 pi over 6, we know our circular definitions want to know what the y value and x value and radius value are for all of these particular values. Now, we've decided to make this a unit circle. We decided to make this circle radius 1. So we know all these r values are going to be 1s, but it would be really nice to know what the coordinates of each one of these points are. Because if we knew the x and y coordinates, we would know the x was the cosine value, the y was the sine value, the tangent would be the y over the x value, and so on. So it would be nice to know those. And luckily, we do, because we know the sides for this triangle. So if you can imagine taking this pi over 6, pi over 3 right triangle, or this 30, 60, 90 right triangle, and kind of turning it over and laying it down, it would fit right here on our circle, where this hypotenuse of 1 is that radius of 1. That's why I like making mine have the hypotenuse of 1. So this short side would be a 1/2 right here. Well, that 1/2 is a y value, 1/2. And this longer side here, that longer side is the square root of 3 over 2. So that longer side is our x value, square root of 3 over 2. So we know those coordinates because we know this triangle. So if somebody asked, what is the sine of pi over 6? The sine of pi over 6, it's the y value, so it should be that 1/2. What's the cosine of pi over 6? Well, cosine of pi over 6 should be the x value, so it's square root of 3 over 2. What's the tangent of pi over 6? Well, it should be the sine over the cosine, so 1/2 over the square root of 3 over 2. Multiply both of those by 2, and we get 1 over the square root of 3, or rationalize it to the square root of 3 over 3. So that's our tangent. And similarly, we could do cosecant, secant, and cotangent. So by knowing this triangle and putting that triangle in this diagram, we can find all the values for pi over 6. But here's the best part. Not only can we find all the ones for pi over 6, if we take that same triangle and instead shift it over so it's here, so almost just picking this up and moving it over there without a lot of rotation, again, that hypotenuse length we know to be 1. So now the short side is the horizontal. So the x value is 1/2. And this y value is our long side, our square root of 3 over 2. So now we can do the same questions for that. Somebody comes along and says, hey, what's the sine of pi over 3? Well, the sine of pi over 3, just square root of 3 over 2. Square root of 3 over 2. Cosine's the 1/2. Tangent would be the square root of 3 over 2 over 1/2, which would reduce it to the square root of 3. Great, so that's 2 of them for one triangle. But also, you may notice that that triangle will also fit here. And here. And here, and here, and down here, and over there. So these values, the 1/2 and the square root of 3 over 2, they're really just going to work their way around all these pi over 6s and pi over 3s. So again, at this 2 pi over 3, the x length here, it's going to be that short side. The only difference is it's going to be negative because we're in quadrant 2. The y value is still going to be that square root of 3 over 2. So square root of 3 over 2. That's the coordinates of that point. So what's the cosine of 2 pi over 3? What's the cosine of 2 pi over 3? Well, it's the x value there, because cosine we associate with those x values. It's negative 1/2. Here, the x is the long value, the negative square root of 3 over 2. And the short value is the y. Complete this diagram. I'm going to give you a couple minutes. Give me a thumbs up when you have it completed. or if you have a question, give me either a thumbs down or a question. But take a minute and find the coordinates of the rest of those pi over 3s and pi over 6s around that circle. Again, you'll find that it's just the 1/2 and the square root of 3 over 2 in different orientations with different positives and negatives. So take a moment to do that. Give me a thumbs up when you got that done. Or show the picture of your happy smiling faces. Yeah, Shay and Sam, you both went back to being shy today. See, hi. Felix, we don't get to see that beautiful long hair of yours. One of you guys should remember I know your mother and I can tell her you're not cooperating. No cam on that PC? All right. I'll take that as a reason. So I got impatient and filled those in. But do you guys have any questions on where those are coming from? Are those making sense? So now, not only if somebody comes around and says, hey, what is the sine of 5 pi over 3? Can we go, okay, 5 pi over 3 we know is down here. So 5 pi over 3, it's the one that's further down, so it's going to be that long edge. So the negative square root of 3 over 2. So not only can we do that, if somebody comes along and says, hey, what is the cosine of, I don't know, 23 pi over 6? Well, you might go, well, 23 pi over 6 isn't on our diagram. Well, yeah, but we know where it is. If we tried to count 23 pi over 6, we know 12 pi over 6 is one rotation, either because 12 pi over 6 would reduce to 2 pi, or we could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So 23 pi over 6 is going to be coterminal to 11 pi over 6. Or we could have said 24 pi over 6 is 2 rotations and then subtract 1. Either way, this is coterminal to 11 pi over 6. So it's going to be the same value as cosine of 11 pi over 6. 23 pi over 6 and 11 pi over 6 are different angles of rotation. One's a lot longer than the other. They're not the same angle, but they have the same terminal side and thus have the same trig values. So the cosine of 11 pi over 6, that's our square root of 3 over 2. Furthermore, let's say somebody came around and asked, what is the, say, sine of pi over 4? Well, pi over 4, we haven't done pi over 4 yet. This triangle doesn't fit in pi over 4. If only we had a triangle that would fit in pi over 4. And those of you who are quietly screaming, we do, we do. This triangle is going to fit in that pi over 4 spot. That triangle, if we lift it up, would fit right in that spot. Because we made this hypotenuse 1, it fits right here. And we know the horizontal and vertical displacements of that. We know this is square root of 2 over 2 in the horizontal and square root of 2 over 2 in the vertical. So what's the sine of pi over 4? It's the y value, because it's sine. So it's the y, square root of 2 over 2. Similarly, we could go, what is the tangent of, let's go with 7 pi over 4. So we got to go, okay, where is 7 pi over 4? 7 pi over 4 is down here in quadrant 4. Again, that same triangle is going to live right there, where that hypotenuse is 1. And those sides are the square root of 2 over 2 and negative square root of 2 over 2, because the y value is negative, thus the sine value is negative in quadrant 4. So the tangent of 7 pi over 4, the y divided by the x, negative square root of 2 over 2 divided by positive square root of 2 over 2 is negative 1. We could even fill in the rest of these. They're all going to be square root of 2 over 2's. What's the only difference going to be? Still square root of 2 over 2 and square root of 2 over 2. But what's got to be adjusted for each one? The negative signs, Matt. Yep, the negative signs, Matt. Just the polarity. Yes, Felix, just the polarity. So negative. They're both negative in quadrant 3. X is negative in quadrant 2. Y is negative in quadrant 4. And they're both positive in quadrant 1. So this is almost, we're almost done with this, what we generally refer to as the unit circle diagram. So you'll often hear people refer to, when they're talking about trig, and I'll say it a lot, but your book will too, and other resources will say, look on your unit circle. This is what is being referred to on your unit circle. It's these standard angles, and this could be either in radians or degrees. We could write in here, if we wanted to, 30 degrees, 45 degrees, 60 degrees, and so on, 120 degrees, and so on all the way around, if we wanted those as well. If you go online and search unit circle, you'll find this. I do recommend printing off a nice one to have as reference. Frankly, I also really strongly recommend drawing this out yourself, building this. Excuse me. Building this in this way. It really will help you own this thing, so you can start seeing it in your head and start building it when you need it, so that when things come up like, hey, what is the sine of any of these things or the cosine of any of these things, we'll be able to come up with those values quickly without breaking our train of thought. But as I said, it's almost that entire tool. There are a couple of little things we're missing. So for example, if I ask what is the cosine of 3 pi over 2, take a minute and decide what that should be based on the diagram. Don't ask a calculator. Don't look it up on a table. Based just on our unit circle diagram and our definitions for the sine, cosine, and tangent, what should the cosine of 3 pi over 2 be? I know you could ask a calculator. That's not what we're trying to do here. Shay says it should be O. Why did you use an O? You don't know? Okay, that's fine. So it should be 0. Anybody want to agree or argue with that, or say, what? That's crazy talk. Yes. And it was fun to pick on her. But Felix, do you want to back her up with the 0 or just make fun of the O? It'd be your guess? Okay. Well, let's look what we do. We go to 3 pi over 2, that angle. We know that the cosine should be the x value of that point of intersection. Well, the nice thing is we don't need a triangle here because we know that point is 1 unit down, 0 units left and right. We know the coordinates of that point should be 0, -1. So the cosine should be the x coordinate. So absolutely, Shay. Oh, sorry. Absolutely, that 0. If we wanted to know what the sine of 3 pi over 2, 3 pi over 2 was, sine would be that -1. What if we wanted the tangent of 3 pi over 2? What's the tangent of 3 pi over 2? Gotta make you guys tell me that. But Shay, you can't type anything. You lost the privilege with the O. No, I just want to hold you back a little bit. Can't divide by 0 for some reason? Felix, you and I have had the divide by 0 conversation. I know you didn't like it, but wait till calculus. You'll be able to divide by 0 a little bit in calculus. But yeah, if we tried to set this up, we'd have the -1 divided by 0, which we know is undefined. So the tangent at 3 pi over 2, there is no tangent value. It is undefined, defined, at 3 pi over 2. Similarly, it's undefined at pi over 2, because pi over 2, our coordinates are 0 and 1. At 0, we'd have, well, it would go the other way. We'd have a 1 and a 0. And over here at pi, we'd have -1 and 0. So we can't find the tangent of 3 pi over 2 or pi over 2, but we can find the tangent of, say, pi radians. Tangent of pi radians, 0 over -1, 0 over -1, which is just 0. So putting in those quadrennial angles, as they're called, the ones that go along the axes. I like to call it the axial angles, but the technical term is quadrennial angles. But nobody uses that word. But nobody that I know of ever use it. Some people write it in books, but no one ever says it. But the axial angles, as soon as we have those values as well, we have a complete unit circle. And this tool is an extremely handy tool once we start talking about what we're going to do with some of this stuff. Usually in Math 112, sometime the middle of this week, I would hand out a quiz that's just, here's a blank piece of paper, draw this. I'd usually give you the circle and the axis, but you'd have to put in all the angles in the standard angles in radians and all these coordinates. I don't make students do that because it's hard. Once you write this out, 10 times or so, filling it out real fast is pretty easy. But the process of having to practice it, the process of building this half a dozen to a dozen times really secures in your head these relationships and really makes a lot of other things faster and easier and quicker. So do take some time when you're, doing something else fairly mindless, make yourself a circle, make yourself some axes, draw these things in there, make it a little neater than this, and, follow those around and put your coordinates in. The 1/3 is going to be short this way, so it's 1/2, long up and down, so square root of 3/2. Because again, in a couple of weeks, we're going to want to be able to have a question that says, hey, find the sine of 4π/3. And without stopping the rest of our thinking process, being able to just go, oh, it's negative square root of 3/2 and keep going, excuse me, is going to be really super important. So work on that, work on these relationships. Cool. Questions about any of that? Nope. It reminds me, Nick, did the calendar did the calendar update for that fix that you know of? Or did you check it yet? I used the email, calendar did not update. Okay, I'll check why again. That link should still continue to work throughout the rest of the term, but I'll try to figure out why that calendar is not updating. Okay. So in the last little while before we go, I do want to, we got another 8 minutes or so. I want to start talking about us graphing our trig functions. And one of the most important things to start keeping in mind when we talk about graphing our trig functions is that this unit circle, however important and helpful a tool it is, this unit circle is not centered right. That unit circle is not the graph of our trig functions. This unit circle is the graph of the circle x² + y² = 1. When we start talking about trying to graph what does y = sine, you could put theta here, but for graphing, we often think of an x just to put x's and y's. So when we start looking at what is the graph of the sine function, what does it look like? It is not this circle. The circle shows us essentially what happens to our trig values as a ray goes around this circle. And it's a great tool because that's how we think of angles going. Angles rotate around. So it shows us the rotation and gives us a nice reference for the values along that rotation. But when we look at trying to graph y = sine x, if that x value or that x-axis is our angle measurements, then our angle is going out along this direction. So we might go through an angle of, say, 90 degrees by the time we get there, 180 degrees by the time we get there, 270 degrees by the time we get there, 360 degrees. So our angle measure is just going out as a numerical value. This isn't supposed to be representing the angle in a physical graphical way. It's just, okay, what happens as I extend the value of that angle? Fair? So what does happen as we extend out? Well, you can probably imagine I'm not going to want to do this in degrees. Lots of reasons why, and we'll talk about some of them as we go along, but certainly we want to get good with this in terms of radian measures. Part of that is radian measures will convert better into talking about things like hours and minutes and days, time scales instead of degree scales. Because radians don't have a unit on them, it's easy to change it into other things without having to bring conversions with time to degrees into the mix. So it's really easier to handle these scales in terms of radians instead of degrees. So one rotation, instead of being the 360 degrees, is going to be our 2 pi radians. So half a rotation, pi, quarter of the rotation, pi over 2, 3/4 of the rotation, 3 pi over 2. And that's our same pi over 2, pi, and 3 pi over 2 that we are familiar with on our circle. So our sine values are going to start repeating every 2 pi. Whatever these values are going to do, as soon as we pass 2 pi, everything's going to be coterminal to something that we just did. So if we know what happens between 0 and 2 pi, we're going to call that 1 period of this function. If we know what happens between 0 and 2 pi, we can just extend that out as far as we want to go. So let's dive in. If we look at an angle of 0, so I want color here. I do like the colors. So if we look at an angle at 0 radians, and we want to know what is the sine at 0, well, sine is the y values. What are the y values when the angle is 0? Well, when the angle is 0, the y value is 0, so that point 0, 0 is going to be on our graph of y equals sine x. Well, great. So let's go up to the next angle we know. The next angle we know conveniently is pi over 6. So if we grab pi over 6 here, well, what was the y value at pi over 6? I ask you that rhetorically because if I wait for you guys to type it in, you're going to make me wait forever because so that y value was fixed, absolutely 1/2. So since that value was 1/2, it's going to go nicely here. Thank you, Martin. Nicely here at 1/2. The next value that we know that would be easy for us to plot would be at pi over 4. So here at pi over 4, that value was, maybe I shouldn't be rhetorical. Maybe I should make you tell me. What was the y value at pi over 4? Well, again, we could back up to our circle. At pi over 4, the y value, the sine value, was root 2 over 2. So the y value there is going to be the square root of 2 over 2. If you want a decimal approximation, it's about 0.7. It's like 0.707. So a little more than a half. So right there. We keep going to pi over 3. Pi over 3, if we checked, the sine of pi over 3 was this square root of 3 over 2. So square root of 3 over 2 is certainly more than square root of 2 over 2, because square root of 3 is bigger than square root of 2. So it's going to be a little higher. It's about 0.89, I think. It's going to be up there. And last part of this quadrant, if we go all the way up to pi over 2, what's the y value? Right there. So what's the sine value? Right there. Sam, good, 1. So up there at 1. So what does our graph look like? Well, our graph is doing that up to a 1. Ooh. Now here's the fun part. If that part makes sense, then as our angles go around into the other quadrants, I look terrible, sorry. I'm getting better at this, but yeah. It's going to go through those same values, right? The y values here are the same. They are square root of 3 over 2, then root 2 over 2, then 1/2, and then down to 0. So it's going to go through those same values. Root 3 over 2, root 2 over 2. This should be more symmetric. Sorry about that. And then 1/2 down to 0. So it's going to go through those same, that's pi, same values curving down in the same shape until it gets to pi. What's it going to do after that? Well, once it goes down into quadrant 2 values after pi radians, it's still the same numbers. Sine would be negative 1/2, negative root 2 over 2, and negative root 3 over 2. So it's the same numbers, but negative. So it's going to go through those same values. They're just going to be negative. Ugh, pi is there. So down to a minimum of negative 1. And then again, that's for those values in this quadrant. Quadrant 4, it's going to match those same y values, this time headed back towards 0. So back towards 0. So each of these kind of 4 arcs are essentially symmetric to each other. This arc is going the opposite direction. These are going down instead. You could think of this, the bump, and that valley being the same if you want. But this is a nice, mine's a little skewed one way. Sorry about that. But this is a very nice, purely symmetric little wave. And that's what our graph of sine looks like. Well, between 0 and 2 pi. What's going to happen after 2 pi, do you think? We're past time, so I'll just tell you guys clearly. But as we go back into our coterminals up here, the coterminals start to repeat those same values. So it's going to do the same thing. It's going to go through that oscillation again and again. If we go in the negative direction, go down here instead, it's going to be coterminal to these values. So it's going to go down this way, that way, and it's just going to continue along. So that's what the graph of our sine function, unmodified, we're going to modify it a whole bunch, is going to look like. It's going to be trapped between +1 and -1 until we start modifying it. And it's going to have one period between 0 and 2 pi. Again, we're going to modify the heck out of this. Before I let you go, I do like people to keep in mind this between 0 and pi over 2, that's between that 0 and pi over 2. This is essentially a map of quadrant 1. These are the values for quadrant 1. After pi over 2, from pi over 2 to pi, that's quadrant 2. So this here, that column, it's not the quadrant 2 of our graph, but it is our quadrant 2 angles. This is where our quadrant 2 angles end up being referenced. Between pi and pi over 3, that's quadrant 3. Between 3 pi over 2 and 2 pi, that's referencing our quadrant 4. After that, we get back to quadrant 1. It's just a coterminal version of quadrant 1. And then quadrant 2 gets mapped again. Then quadrant 3 gets mapped, and so on. Back this direction, out to negative pi over 2. That's quadrant 4 again when we go into negative. So this is quadrant 4 mapping again. So keep this in mind. Often you'll hear people refer to and say, hey, this is quadrant 3 happening. And people will go, that's not quadrant 3, that's in quadrant 4. Talking about the referencing where that angle is. Cool? Okay. So tomorrow we'll start playing with this in terms of modifying this, having its period be something other than 2 pi, something other than 6.28. What if we want this thing to oscillate every, say, 10 minutes instead of every 6.28 minutes? What if we want it to be higher and lower? How do we modify this? We'll talk about that tomorrow. Anything you guys need before you trundle off about your day? Nope. Okay. You're very welcome. I will tell your mother if you don't start cooperating with the camera. Not you, Martin. Just to pick on her, if nothing else. Okay. So if something does come up that you guys need, let me know. And have a wonderful day.